Far out beyond the reef, where sunlight breaks into blue shafts and the seafloor fades into deeper color, a green sea turtle moves with the calm of something that has never needed to hurry through history. Its front flippers pull slowly through the water, each stroke wide and deliberate, as if the ocean itself is familiar ground. Around it, small fish flash over coral heads, seagrass bends in the current, and the surface above glitters like a distant ceiling. Nothing about the turtle looks urgent. That is part of its power. It carries the shape of an animal that has survived by moving through time at the speed of patience. Sea turtles have been crossing the oceans for more than 100 million years. Their ancestors lived alongside dinosaurs and great marine reptiles, moving through seas that held creatures now known only from fossils. When the mass extinction at the end of the Cretaceous erased the non-avian dinosaurs and many marine giants, sea turtles survived. The green sea turtle swimming through a modern reef is not the same species that moved through those ancient oceans, but it belongs to a lineage that passed through one of the greatest disasters in Earth's history. Its body is a quiet reminder that survival is not always loud. Sometimes it is a shell, a long migration, a slow metabolism, and the ability to keep returning. The green sea turtle is built differently from a land turtle. Its shell is not a heavy dome for crawling through grass or forest. It is a streamlined shield shaped for water. The limbs are no longer walking legs in the usual sense, but flippers, broad and powerful enough to carry the animal across entire ocean basins. On land, the turtle becomes awkward, dragging itself with effort across sand. In the sea, that same body becomes graceful. The ocean gives it back its design. Every slow stroke of the flippers shows the truth of the animal. It is not clumsy. It is only misplaced when removed from water. Much of its adult life may be spent in coastal feeding grounds, especially where seagrass meadows and algae grow. This is one of the green sea turtle's most important ecological roles. Adults are largely herbivorous, cropping seagrass and helping keep underwater meadows healthy and productive. A seagrass bed may look quiet, but it is a living nursery for fish, crustaceans, mollusks, and countless small animals. By grazing, turtles can influence how these meadows grow, preventing old growth from choking younger shoots and helping maintain a habitat that supports many other species. The turtle is not only passing through the ecosystem, it is shaping it with every mouthful. That feeding is steady, almost peaceful, but the life of a green sea turtle begins in violence and risk. On a warm beach at night, a female hauls herself from the surf with immense effort. The same flippers that carried her so easily through the sea now dig and drag through sand. Each movement costs energy. She crosses the beach slowly, chooses a nesting place above the tide line, and begins to dig with her rear flippers. The nest chamber forms in darkness, hidden beneath her body. Then the eggs drop one by one into the sand, soft-shelled and pale, carrying the next generation into a world where most will never survive. The beach is where the turtle story becomes almost unbelievable. A female may return after decades at sea to nest in the same general region, and often near the same beach, where she hatched. The ocean between those two events is enormous. As a hatchling, she would have scrambled from the sand, crossed a dangerous open beach, and entered the surf among fish, crabs, birds, and waves. Then she vanished into years of ocean life. Somehow, after growing, feeding, migrating, and surviving long enough to mature, she can find her way back toward the coast where her life began. Part of that navigation appears to involve Earth's magnetic field. Sea turtles can detect magnetic information and use it as a kind of map and compass across the ocean. The idea sounds almost impossible because humans experience navigation mostly through landmarks, memory, stars, and instruments. A sea turtle experiences the planet differently. Magnetic signatures vary across the globe, and young turtles may imprint on the magnetic character of their natal area. Later, when the time comes to reproduce, those hidden cues may help guide them back. The beach is not just a place, it is a magnetic address written into the animal's life. This does not mean every turtle returns to a single exact footprint in the sand. Beaches shift, storms reshape coastlines, magnetic fields drift over time, but the pattern is still extraordinary. A creature that left as a hatchling smaller than a human hand can return as an adult to the same stretch of coast after years of crossing open water. There is no road, no visible path, no simple memory of landmarks from infancy. There is only the ocean, the current, the field of the planet, and an inherited system refined through deep evolutionary time. The eggs beneath the sand carry another strange truth. In sea turtles, sex is not determined by chromosomes in the way it is for humans. It is shaped by temperature during incubation. Cooler nests tend to produce more males. Warmer nests tend to produce more females. The future balance of a population can be influenced by something as simple and fragile as the heat held in a beach. Shade, sand color, rainfall, nest depth, season, and climate all matter. A few degrees can change the lives hidden underground before they ever see the sea. This makes the nesting beach more than a birthplace. It is an incubator, a compass point, and a climate-sensitive nursery. For an animal that survived ancient extinction, the modern world presents a different kind of test. Beaches can be disturbed by development. Artificial lights can confuse hatchlings, rising seas can flood nests, and warming sand can alter sex ratios. The green sea turtle carries a body plan old enough to outlast vanished marine reptiles, but its future still depends on strips of sand that can be damaged in a single generation. When the hatchlings finally emerge, usually at night, the beach becomes a race they do not understand, but must immediately win. Tiny turtles push through the sand together, then move toward the brightest natural horizon, which should be the open sea, reflecting moonlight and starlight. Every meter is dangerous. Crabs wait in the dark. Birds may arrive at dawn. Fish patrol the shallows. Even after reaching the water, the young turtle enters a much larger wilderness. Survival is so unlikely that the species relies on numbers, timing, and persistence. Many eggs are laid because so few lives will continue. Those that do survive disappear into years that are still difficult for humans to follow completely. Young turtles drift, feed, grow, and eventually recruit into coastal habitats. The soft hatchling becomes a large marine reptile with a hard shell, powerful flippers, and a memory of movement older than the coastline itself. Its life is stretched across scales most animals never touch. The nest chamber, the reef, the seagrass meadow, the open ocean, the magnetic field of Earth. As the adult turtle rises for air, its head breaks the surface for only a moment. A breath enters the lungs, and then it slips below again, returning to the blue quiet. It has no roar, no claws built for attack, no dramatic display. Its survival is written in endurance. The green sea turtle is not a relic because it is unchanged. It is a survivor because its way of life has remained powerful across impossible time. Hatch on land, trust the horizon, vanish into the ocean, read the invisible field of the planet, and one day return. That is what makes it one of the great ancient animals of the sea. It connects the beach to the open ocean, the present to the Cretaceous, and a single nest of warm sand to the future of an entire population. After all the giants that disappeared, after all the oceans that changed, the green sea turtle still moves through the water with that slow, deliberate grace. It does not look like an animal that beat extinction. It looks like an animal that never stopped swimming. Above a still wetland in northern Australia, the air looks empty until something cuts through it with impossible precision. A dragonfly hangs over the water, its body thin as a needle, its wings catching flashes of blue, green, and glass-clear light. It does not drift like a butterfly or buzz clumsily like a fly. It stops, shifts sideways, rises, drops, and reverses, as if the normal rules of flight are only suggestions. For a moment, it hovers over the reeds like a tiny machine built from sunlight and nerve tissue. Then it vanishes forward, and a mosquito that was alive a heartbeat earlier is gone. The dragonfly is small enough to be ignored by most people walking past a pond. That is almost funny, because in the history of flight, animals like this were among the first true masters of the air. Long before birds existed, before pterosaurs ruled the skies, and before dinosaurs had even appeared, ancient dragonfly-like insects were already hunting over swampy forests. Around 300 million years ago, in the Carboniferous world, the air above wetlands belonged to giant winged predators. Some of their extinct relatives, such as Meganeura and other griffinflies, reached wingspans of roughly 65 to 70 centimeters. That is not a delicate insect anymore. That is something closer to a hawk-sized shadow crossing prehistoric water. Modern dragonflies are much smaller, but they carry the same deep idea. The air is not empty space. It is hunting ground. Their bodies are built around aerial control in a way few animals can match. Each of the four wings can move with a level of independence, allowing sudden turns, hovering, backward flight, sideways movement, and rapid acceleration. Where many flying animals must keep moving forward to stay in control, a dragonfly can pause in mid-air and wait. It can inspect a patch of reeds, hold position against a breeze, then change direction so sharply that the movement feels less like flying and more like thinking made visible. That control matters because the dragonfly is not a casual hunter. It is one of the most efficient predators on Earth. Studies of dragonfly hunting have recorded capture success rates that can reach around 95% or even higher under certain conditions. Lions miss often. Sharks miss often. Many predators live with failure as part of the job. A dragonfly, by contrast, can turn the air into a trap with frightening accuracy. It does not simply chase prey from behind, it predicts movement, intercepts angles, and arrives where the prey is about to be. The key to that precision begins with the eyes. A dragonfly's head is dominated by huge compound eyes, each built from thousands of tiny visual units called ommatidia. In some species, the number can approach around 30,000 across the eyes, giving the animal an almost panoramic awareness of the world around it. It does not see like a human looking through two forward-facing windows. It sees as a creature surrounded by motion. Above, below, beside, behind, the environment is constantly being scanned for tiny changes. A small insect crossing the sky does not simply pass through its vision, it becomes a moving point in a living map. This is why the dragonfly feels so advanced, even though its lineage is so ancient. It is not ancient because it is simple, it is ancient because it found a solution that kept working. Its nervous system processes visual information with extreme speed, allowing it to lock onto prey, adjust its wing beats, and calculate an interception path in fractions of a second. To us, a midge or mosquito seems too small and erratic to track. To a dragonfly, that same insect is a target with direction, speed, and future position. The hunt is not a race, it is geometry. When it strikes, the dragonfly's legs swing forward like a basket. The prey is caught in mid-air, often without the dragonfly needing to land. Small insects may be eaten on the wing, held between the legs, while the jaws begin their work. There is no dramatic struggle that lasts long enough for the human eye to enjoy. The efficiency is the drama. The dragonfly crosses a distance, the wings flicker, the legs close, and the wetland loses another mosquito. In a place where tiny flying insects breed in huge numbers, this kind of predation is not a detail. It is part of the system that keeps the air from becoming overwhelming. But the dragonfly's life does not begin in the sky. Before it becomes an aerial hunter, it is a predator underwater. Dragonfly nymphs live beneath the surface in ponds, streams, swamps, and flooded vegetation, where they hunt small aquatic animals with a different kind of weapon. Their lower mouthpart can shoot forward like a hinged mask, grabbing prey before it can escape. Mosquito larvae, tadpoles, small fish, and other invertebrates can all become food. So the adult dragonfly is not a gentle creature that suddenly becomes dangerous after learning to fly. It is a predator from the beginning, changing worlds as it grows. That transformation is one of the most remarkable parts of its life. A nymph that has spent months or even years underwater eventually climbs onto a reed or stem. Its outer skin splits, and the adult pulls itself free, soft and pale at first, with wings crumpled and useless. Slowly, fluid expands the wings, the body hardens, the colors deepen. The animal that belonged to mud, stems, and submerged shadows becomes a creature of open air. It is not just growth. It is a complete change of element, from underwater ambush to aerial pursuit. Temperature shapes this life as much as vision and wings do. Dragonflies need warmth to fly well, so they often become most active when sunlight heats their bodies and the insects around them. Some perch with wings spread, absorbing heat. Others patrol sunny edges where prey is active and the air currents are useful. In cooler moments, their precision fades. In strong warmth, they become sharper, faster, and more dangerous. The wetland is not just a background. It is a system of heat, water, insects, light, and timing, and the dragonfly reads all of it. Some species also move across surprising distances, following seasonal water, food, and breeding opportunities. The most famous migrations show how a creature that seems tied to one pond can actually be part of a much larger pattern, crossing landscapes as wetlands appear and disappear. Rain creates temporary nurseries. Heat accelerates insect life. New generations rise from water and fill the air. The dragonfly is both local and ancient, delicate and relentless, tied to one reed in one moment and to deep evolutionary history in the next. Predators still take them. Birds snap them out of the air. Frogs and fish catch them near water. Spiders trap the careless. Even the hunter with nearly all-around vision is not safe in every direction at every second. But that danger only makes its precision more important. A dragonfly cannot afford to be slow. It cannot afford to waste every chase. Its body is built for a world where the air is full of opportunities and threats at the same time. By late afternoon, the wetland glows gold, and the dragonfly returns to a reed above the water. It looks fragile there, like a shard of colored glass resting on a stem, but that fragile shape carries one of the oldest hunting stories on Earth. Before dinosaurs shook the ground, before birds filled the sky, Before mammals became important in the night, insects had already discovered flight, vision, interception, and aerial killing. The dragonfly is not impressive because it is big. Its giant relatives had that chapter. The modern dragonfly is impressive because it became small without becoming weak. It kept the speed, the eyes, the control, and the killer accuracy. It is a tiny predator with a prehistoric shadow, proof that sometimes the oldest designs are still the sharpest in the air. At the edge of a northern Australian river, the world does not feel fully modern. The air is heavy with heat, mangrove roots twist into black mud, and the water moves so slowly that every shadow looks permanent. Small fish flicker between submerged branches. Insects touch the surface and leave tiny rings that spread outward, then vanish. For a long time, nothing seems to happen. Then one of the logs near the bank opens an eye. This is the saltwater crocodile, and few animals make the past feel so close. People often call it a living dinosaur, and while crocodiles are not dinosaurs in the strict scientific sense, the comparison is easy to understand when one is lying almost motionless in front of you. Crocodilians come from an ancient reptile line that has existed for more than 200 million years. Their ancestors shared the planet with dinosaurs, survived the extinction that ended most of those giants, and kept moving through a world that changed around them again and again. The animal in this river is not a frozen fossil. It is something more powerful than that. A design that has been tested by deep time and still works. The saltwater crocodile is the largest living reptile on Earth. A big male does not simply look large. He changes the scale of the river around him. His skull is broad and heavy, his back is armored with bony plates, and his teeth are shaped less like blades and more like locking pegs. They are not made for clean slicing, they are made for holding. Once those jaws close, escape becomes a problem of pressure, leverage, and breath. Saltwater crocodiles have produced the strongest bite forces ever directly measured in any living animal. But the true danger is not only the force itself. It is what that force allows the crocodile to do next. Almost everything about its body is built around ambush. The eyes, ears, and nostrils sit high on the skull, allowing most of the animal to disappear beneath the surface while it still watches, listens, and breathes. From above, it may show only a narrow strip of head and ridged back. Below the water, the real mass waits hidden. The thick tail holds the power. The limbs, awkward looking on land, become stabilizers underwater. The whole body becomes a silent engine, saving energy until one sudden movement turns still water into violence. That is what makes the saltwater crocodile such a dangerous predator at the border between land and water. Every animal that comes to drink must make a small compromise. It lowers its head. It focuses on the surface. It places its feet on unstable mud. It enters the crocodile's world for just long enough to survive the drink. A wallaby, a feral pig, a bird, a turtle, a fish, even another crocodile. Anything that repeats the wrong habit at the wrong bank becomes part of the river's calculation. When the attack comes, it can look impossible from an animal that seemed almost asleep. The water erupts, the head lifts, the jaws close, and the prey is pulled toward the one place where strength begins to fail. On land, an animal can kick, turn, push, scramble, and breathe. In water, those choices disappear quickly. The crocodile does not need to chase for long. It needs to break balance, steal direction, and drag the struggle below the surface. Panic burns oxygen fast. Every twist makes it harder for the prey to know where the air is. This is where the death roll becomes more than a frightening image. It is not random rage, it is mechanics. By spinning its entire body, the crocodile uses mass, rotation, and leverage to disorient, prey, tear tissue, and break resistance. In shallow water, against mud, roots, or submerged branches, the roll can turn the environment itself into part of the attack. The crocodile's body becomes a wrench, the river becomes the grip, the bank becomes the brace. For an animal built to fight on solid ground, that change of rules can be fatal. And yet the same predator that can explode with such force may spend most of the day appearing almost inactive. This stillness is not laziness, it is biology. Crocodiles are ectotherms, relying heavily on external heat to regulate body temperature. In the morning, a crocodile may bask on the bank, warming its body in the sun. During intense heat, it may slide back into the water or rest in shade. Its open mouth may look like a threat, but often it is part of temperature control. Unlike mammals, which spend constant energy keeping their bodies warm, crocodiles can live on a slower energy budget. After one large meal, a crocodile can survive for months without eating. In a harsh environment, patience is not just behavior, it is survival economics. That slow metabolism changes the rhythm of the predator. A crocodile can afford to wait. It can miss today and still be dangerous tomorrow. It can remain near a crossing point, a muddy drinking edge, or a tidal creek until prey behavior repeats itself. This is why a large crocodile becomes more than an animal in the landscape. It becomes a pressure point. Birds choose landing places differently. Mammals hesitate near the bank. Even when the crocodile is not visible, its possibility changes the way other animals move. The most unsettling part is that the crocodile's stillness is not blindness. Along the snout and jaws are tiny dark sensory dots called integumentary sensory organs. They look like small pores in the skin, but they are part of an extraordinary detection system. In water, they register minute pressure changes and vibrations. A fish flicking its tail, a bird touching down, a mammal stepping into the shallows. Each movement sends information across the surface. The crocodile reads those signals through its face. Darkness does not make the river empty. Muddy water does not blind it. The water becomes a sheet of information, and every ripple may reveal life nearby. This gives the crocodile an advantage that feels almost unfair. At night, when the river turns black and the banks lose their shape, the crocodile still has ways to sense what is moving around it. A careless splash is not just sound, it is location. A repeated drinking path is not just habit, it is opportunity. The crocodile does not need to understand the river the way we do. It understands the version of the river that matters to an ambush predator. Despite its name, the saltwater crocodile is not limited to the sea. It moves through freshwater rivers, mangrove channels, tidal estuaries, coastal lagoons, and open water. Salt glands help it deal with marine conditions, allowing it to travel between river systems and along coastlines. This mobility is part of its success. It can use habitats that many animals experience as separate worlds. Rivers, tides, swamps, and coastlines are not barriers to it. They are connected hunting grounds. But the giant at the riverbank did not begin life as a ruler. Young crocodiles are vulnerable from the start. Eggs can be lost to flooding, heat, or predators. Hatchlings may be taken by birds, fish, monitor lizards, and even larger crocodiles. The massive adult that now controls a stretch of river is a survivor of many dangers. His size is not just growth, it is evidence. Every scar across his armored hide carries the history of fights, failed hunts, storms, droughts, and years of waiting. In the ecosystem, the saltwater crocodile is not simply a monster, it is a force that shapes behavior. By taking exposed, sick, slow, or careless animals, it moves energy through the food web. Its kills feed scavengers. Its presence keeps animals alert. Fear itself becomes part of the ecology. A river with a large crocodile is not just more dangerous, it is more awake. As the light fades, the crocodile sinks again until only the eyes remain. The river looks peaceful, and that is the final trick. The saltwater crocodile does not need to dominate every second of the scene. It lets the landscape hide it. It turns stillness into camouflage, hunger into patience, and a single ripple into a signal. This is why it makes such a powerful beginning. It is not frightening because it belongs to the past. It is frightening because it still belongs completely to the present, one of evolution's most enduring answers to life at the water's edge. In the Australian bush, not every ancient animal looks like it belongs in a monster scene. Some arrive quietly, pushing through leaf litter with a blunt snout, short legs, and a body covered in spines. At first glance, the echidna can look almost harmless, even a little awkward, as it shuffles between grass stems and fallen bark. It does not have the cinematic menace of a crocodile or the sudden theater of a frilled lizard. It does not slice through the air like a dragonfly. But this small, stubborn mammal carries one of the strangest evolutionary stories in Australia. It is not a reptile pretending to be ancient. It is a mammal that still keeps a doorway open to a much deeper past. The echidna is a monotreme, one of the rare egg-laying mammals. That one fact already bends the normal idea of what a mammal should be. Mammals are usually defined in the public imagination by live birth, warm bodies, fur, and milk. The echidna complicates that picture. It has fur hidden between spines. It feeds its young with milk. It is warm-blooded, though in a slower and more flexible way than many mammals. Yet the female lays a leathery egg, carries it in a temporary pouch, and raises a young so undeveloped that it feels almost unfinished when it hatches. The baby echidna is called a puggle, a name that sounds almost too soft for an animal born into such a tough landscape. That softness does not last. An adult echidna is built for a life close to the ground, where survival is measured in digging, sensing, conserving energy, and refusing to be easy prey. Its spines are modified hairs, hardened into a defensive coat that can turn the body into a living pincushion. When danger approaches, the echidna does not try to outrun it across open ground. It digs. It wedges itself into soil, roots, or leaf litter with surprising strength, exposing a shield of spines while protecting its softer underside. If the ground is loose, it can seem to sink into the earth, leaving a predator with little more than sharp points and frustration. This defense makes sense because the echidna is not built around speed, it is built around persistence. Its limbs are powerful, with strong claws designed for tearing into ant nests, termite galleries, and soil. A log that looks solid to another animal may be full of food to an echidna. A termite mound is not just a mound, it is a living structure with tunnels, chambers, moisture, and thousands of bodies moving inside. The echidna approaches this hidden world with the focus of a specialist. It presses its snout into cracks, digs with deliberate force, and searches for movement that most animals would never notice. The feeding system is wonderfully strange. Echidnas have no teeth. They do not bite and chew in the familiar mammal way. Instead, they use a long, sticky tongue to gather ants, termites, and other small prey. Food is pulled into the mouth and crushed against hard pads on the tongue and the roof of the mouth, grinding insects down without teeth at all. It is a reminder that evolution does not have one correct design for being a mammal. The echidna does not need jaws full of teeth if the tongue, snout, claws, and mouth pads all work together. Its whole head is shaped around entering narrow spaces and harvesting the small lives hidden inside. The snout is more than a nose. It is a sensory instrument. Like the platypus, the echidna has electroreceptors, though in a much more modest form. These receptors can help detect tiny electrical signals associated with prey movement, especially in damp soil or rotting wood where insects and larvae are active. Combined with smell and touch, this gives the echidna a way of reading the ground that feels almost alien from a human point of view. We look at dry leaves, bark, and dirt. The echidna investigates a layered world of scent, pressure, moisture, and faint biological signals. Its landscape is not empty. It is full of buried information. This is where the echidna's ancient character becomes more interesting than simply calling it a relic. It is not a failed version of a modern mammal. It is a successful answer to a different question. How do you survive in a continent where food can be scattered, temperatures swing hard, fires reshape the land, and predators may appear from above, behind, or under cover? The echidna's answer is not speed or aggression. It is flexibility. It lowers its demands on the world. It eats small prey that are widely available. It shelters when conditions become harsh. It slows itself down when energy is difficult to find. That ability to slow down is one of its most remarkable adaptations. Echidnas can enter torpor, reducing body temperature and metabolism to save energy. In cold conditions, this helps them survive when activity would cost too much, but the same physiological flexibility can also matter after fire. A bushfire changes everything quickly. It burns cover, removes food sources, heats the soil, and leaves the landscape exposed. Echidnas may survive the immediate danger by sheltering in logs, burrows, or protected spaces, but survival after the flames can be just as difficult. With fewer insects active and less cover available, lowering metabolism becomes a way to endure the shortage. The animal does not defeat fire, it outweights the aftermath. There is something deeply Australian about that strategy. This is a continent where extremes are part of the rhythm. Drought, heat, cold nights, flood, fire, and sudden abundance after rain. The echidna belongs to that rhythm because it does not rely on one perfect condition. It can move through forests, woodlands, heathlands, grasslands, and arid country. It may be seen crossing roads, nosing through gardens, climbing over rocks, or disappearing into scrub. Its body looks specialized, but its lifestyle is surprisingly broad. It is a small animal with a wide map. Reproduction brings the story back to its strangest point. The female lays a single egg into a temporary pouch. When the puggle hatches, it is blind, tiny, and helpless, clinging inside the pouch and feeding on milk that seeps from specialized patches of skin rather than from teats. For a mammal, this is a deeply unusual beginning. The puggle stays protected until its spines begin to develop, which creates a very practical problem for the mother. A soft baby can be carried against the body. A growing ball of needles cannot. Eventually, the young is moved to a nursery burrow where the mother returns to feed it until it is ready for independence. That slow, hidden childhood makes every adult echidna feel more impressive. The animal crossing the dry ground has already passed through a fragile egg stage, a helpless pouch stage, and a vulnerable burrow stage. It has avoided goannas, birds, foxes, dogs, cats, roads, drought, and heat. Its survival is not dramatic in the obvious way, but it is hard-earned. The echidna's life is a quiet argument against judging animals by speed or size alone. As evening settles, the echidna moves under a fallen log and begins to dig again. Dust gathers on its spines. Its snout works slowly through the soil, following a smell, a vibration, or perhaps a faint signal from prey hidden below. It does not look like a beast from the age of giants. It looks smaller, stranger, and more patient than that. But in its egg, its pouch, its toothless mouth, its electroreceptive snout, and its ability to lower the flame of its own body, the echidna carries a version of mammal history most of the world has lost. The twist is that ancient does not always mean huge. It does not always roar, strike, or dominate the screen. Sometimes ancient walks low through the leaves, eats termites with a sticky tongue, raises a puggle in a pouch, and survives by becoming very hard to kill. The echidna is not impressive because it seems unfinished. It is impressive because it proves there was more than one way to become a mammal, and this strange spiny path is still alive. Far off the southern coast of Australia, the ocean changes character. The water is colder here, darker and heavier, rolling over deep channels where seals move between island rocks and kelp forests sway below the surface. Sunlight enters the water in broken sheets, fading quickly into blue-green shadow. From above, the sea may look empty. From below, it is full of signals, pressure changes, scent trails, struggling fish, distant movement, and the faint electrical traces of living bodies. Somewhere beyond the visible edge of the reef, a great white shark turns slowly through the gloom. This is the final animal because it carries the deepest shadow of all. The great white itself is not 450 million years old as a species, but sharks as a lineage reach back roughly that far. That means shark-like animals were already moving through Earth's oceans before dinosaurs existed, before flowering plants, before mammals, and even before true forests had taken over the land. Trees feel ancient to us because they tower over human time, but sharks are older than the world that made trees common. Some estimates have even made sharks older than Saturn's rings, although the true age of those rings is still debated. The comparison is almost unnecessary. Sharks were already here when life on land was still learning how to become the world we recognize. That age does not mean sharks are primitive. It means they have been edited by survival for an almost unimaginable length of time. A great white shark is not a leftover monster from a cruder Earth. It is a highly refined predator shaped by speed, sensitivity, endurance, and precision. Its body is built like a living blade, heavy through the middle, narrow toward the tail, with a pointed snout and powerful crescent-shaped caudal fin that drives it through the water. The white underside helps it blend with bright surface light when viewed from below, while the darker back makes it harder to see from above. Even its colors are part of the hunt, turning open water into camouflage. One of the strangest facts about a shark is hidden inside the body. It has no true bones. Its skeleton is made of cartilage, the lighter, flexible material humans have in the nose and ears. In a large shark, that cartilage can be strengthened with mineral deposits, but it is still not bone in the way a mammal or reptile carries bone. This matters because the ocean rewards different engineering. A cartilaginous skeleton can be lighter and more flexible, helping the shark move with power without carrying the dense weight of a bony frame. The great white looks solid, almost armored by reputation, but inside it is built around a different solution: strength without the same kind of skeleton land animals depend on. Its muscles and body shape give it speed, but the true horror of the great white is not only how it moves, it is how it senses. The ocean hides things from human eyes. Darkness arrives early underwater. Mud, distance, waves, and depth can erase visibility. But the shark does not rely on sight alone. It smells. It feels vibration through the lateral line, a sensory system that detects movement and pressure changes in the water. It watches contrast and silhouette. And near the snout, in small pores called the ampullae of Lorenzini, it has an electrical sense that opens an entirely different layer of reality. Every living animal gives off weak electrical signals. Muscles contract, nerves fire, hearts beat. To us, these signals are invisible and unreachable without instruments. To a shark at close range, they can become information. The ampullae of Lorenzini allow sharks to detect faint electric fields in seawater, helping them locate prey even when visibility is poor. It is not magic, and it is not vision in the human sense, but functionally, it lets the shark sense life where eyes alone would fail. A wounded fish hidden in shadow, a ray buried under sand, a seal moving in dim water. The body betrays itself simply by being alive. This makes the great white feel almost unfairly equipped. At distance, smell and movement can draw it toward an area. Closer in, shape and contrast help define the target. At the final range, electrical sensitivity can confirm what the water is hiding. The shark does not need one perfect sense, it layers them. The ocean becomes a three-dimensional field of clues, and the shark reads those clues with a brain and body built for predation. The famous attack from below is not blind violence. It is an ambush shaped by position, speed, and timing. A seal at the surface is outlined against light. The shark rises from below, where its darker back is swallowed by depth, and turns vertical space into a weapon. Yet even here, the story is not just about attack. Great whites are part of a larger marine system, and their presence can shape the behavior of animals around them. Seals use haul-out sites, kelp edges, and group movement in ways that reduce risk. Fish scatter from sudden pressure. Scavengers benefit from what large predators leave behind. A top predator does not only remove prey, it changes how prey uses space. Fear becomes part of the architecture of the ecosystem, just as it does along crocodile rivers, but in the ocean, that architecture is invisible. It is made of depth, distance, current, and memory. The great white is also warmer than many people expect. It is not warm-blooded like a mammal, but it can retain heat in parts of its body through specialized blood vessel arrangements. This regional warmth helps power muscles, digestion, and activity in cooler water. In a cold sea, that advantage matters. It allows the shark to move through habitats that would slow many other fish. The body is not simply floating through the ocean at the mercy of the water temperature. It is managing heat in a way that expands where and how it can hunt. Its life history adds another kind of tension. Great whites grow slowly, mature late, and produce relatively few young compared with many fish. A predator this powerful is not produced quickly by the ocean. Each adult represents years of survival through a dangerous early life, changing diets, competition, and human pressure. Young great whites may feed more on fish before taking larger marine mammals as they grow. The enormous adult that appears so dominant in deep water began as something vulnerable enough to be hunted itself. Apex predators often look inevitable only after they have survived the years when they were not. That is why the deep history of sharks should not make them seem invincible. Their lineage has survived 5 mass extinctions, but survival through the past does not guarantee safety in the present. Modern threats can move faster than evolution can answer. Overfishing, bycatch, habitat disruption, and the removal of prey from marine systems. A body plan that passed through ancient planetary disasters can still be threatened by a few human generations. That contrast is almost impossible to ignore. An animal older than forests can be endangered by the speed of the modern world. Still, when a great white passes beneath the surface, it is hard not to feel the weight of what it represents. The fin cuts through cold water, the gills pulse. The tail moves with controlled force. There is no need for exaggeration. The real animal is already more impressive than the monster we invented around it. It has no bones, yet it dominates open water. It has no need for daylight, yet it can detect the hidden electricity of life. It belongs to a lineage that was here before dinosaurs rose, before they vanished, and before humans were even a possibility. As the shark disappears into deeper blue, the ocean closes behind it as if nothing was ever there. That is the perfect ending. The oldest power in this episode is not the loudest, not the strangest looking, and not the most theatrical. It is a silent shape, moving through darkness, built from cartilage, guided by electricity, and sharpened by nearly 500 million years of survival. The great white shark is not a creature from the past. It is the past still hunting in the present. In the dry woodlands of northern Australia, the forest does not always announce danger with teeth. Sometimes it announces it with theatre. The morning heat rises slowly through the eucalyptus trees, turning the bark pale and silver, while cicadas grind their sound into the air. Termite mounds stand like weathered towers between the grasses, and the ground is scattered with leaves so dry they crack under the smallest footstep. On one tree trunk, almost invisible against the rough bark, a frilled lizard holds itself flat and still. Its body is slender, its claws hooked into the wood, its long tail hanging like a line of shadow. For now, it looks ordinary enough to miss. That is the first trick. Before it becomes a spectacle, the frilled lizard is a master of not being noticed. Its colors blend into the woodland around it, browns, grays, oranges, and muted earth tones that match bark, dust, and dead leaves. It spends much of its time on tree trunks, watching the ground below for insects and watching the sky above for birds. In this world, survival often begins before the chase. The animal that is not seen does not have to run. The animal that matches the tree becomes part of the tree. But if a predator comes too close, the quiet reptile suddenly becomes something completely different. The mouth opens wide. A large circular frill bursts outward around the head. The body rises, the throat darkens. In one instant, a slim lizard that looked barely larger than a branch becomes a flashing, open-mouthed warning sign. The transformation is so sudden that it feels almost prehistoric, as if some small forest dinosaur has stepped out from behind the bark and remembered how to frighten the modern world. This is why the frilled lizard is so powerful visually. It does not need to be large to feel dramatic. Its defense is built around surprise, contrast, and timing. A snake, a goanna, a bird of prey, or a curious mammal may approach expecting a small, manageable reptile. Instead, it receives a sudden burst of size and color. The frill frames the head like a shield. The open mouth adds a flash of pink and yellow. The body may rock forward, the tail stiffens, and the lizard can even rush toward the threat for a moment before turning and escaping. For a predator making a split-second decision, that hesitation can be enough. The frill itself is not just loose skin hanging from the neck. It is supported by long rods of cartilage connected to the jaw. When the lizard opens its mouth, the mechanics of the head help spread the frill outward, turning a hidden fold into a sudden display. It is a beautifully efficient piece of anatomy because the act of threatening and the act of opening the display are connected. The lizard does not need to think through each part separately. Mouth opens, frill rises, body looks bigger. In survival terms, that kind of automatic performance matters. There may be no time for careful decisions when a predator is already within striking distance. And the strange part is that the entire performance is mostly bluff. The frilled lizard is not venomous. It is not built to overpower large enemies. Its jaws can bite and its claws can grip, but its display is not a promise of real domination. It is an argument. It is trying to convince danger that the cost of attack might be higher than expected. In nature, bluff is not weakness. Bluff is strategy. Many predators cannot afford injuries from prey that fight back, and they often avoid targets that seem uncertain, noisy, confusing, or larger than they first appeared. The frilled lizard survives by briefly becoming a question mark. If the bluff fails, the second act begins. The lizard turns and runs, often lifting its front body high and sprinting on its hind legs toward the nearest tree. That bipedal dash is one of the reasons it feels so dinosaur-like to human eyes. The body tilts upright, the tail balances behind, and the small reptile races across the ground with a strange, urgent confidence. It is not trying to look elegant, it is trying to reach vertical safety. A tree trunk is more than a hiding place. It is an escape route, a lookout tower, a hunting platform, and a thermal refuge all at once. Most of the frilled lizard's life is quieter than its famous display. It feeds largely on insects and other small animals, waiting on trees before dropping to the ground to seize prey. Ants, termites, beetles, spiders, and smaller invertebrates all become part of its diet. This makes the lizard a small but important predator in the woodland system, taking advantage of the huge insect life that drives much of northern Australia's ecology. Termites build the mounds. Insects feed birds, reptiles, and mammals. Lizards like this one turn that hidden abundance into muscle, eggs, movement, and survival. Heat shapes every part of its day. Like other reptiles, the frilled lizard depends heavily on external temperature to regulate its body. Morning sun helps raise its body temperature enough for movement, hunting, and digestion. Too much heat, however, becomes dangerous, so shade and tree cover matter. The lizard's daily routine is a careful negotiation with the sun. Warm enough to move well, cool enough not to overheat. A mammal can burn internal energy to keep a stable temperature, but a lizard must read the landscape differently. Sun patches, shaded bark, wind, soil, and tree height all become part of its survival map. Season also changes the rhythm of its world. During wetter periods, insect activity increases, vegetation thickens, and food becomes more available. Breeding becomes tied to these cycles of heat and rain because young reptiles need a world rich enough to support growth. Eggs laid in the ground depend on temperature, moisture, and protection from predators. The dramatic adult on a tree trunk is the result of many hidden risks that came before it. An egg that did not dry out, a hatchling not found by a predator, a young lizard fast enough to reach cover again and again. Its predators are not imaginary. Raptors can strike from above. Snakes can move through branches and grass. Monitor lizards can investigate trunks and hollows. Feral cats and other introduced predators add extra pressure in some habitats. Against these enemies, the frill is not a magic shield. It is one tool among several. Camouflage first, stillness second, display third, escape last. The order matters. The frilled lizard does not want to perform unless it has to. A display is useful, but it also reveals the animal completely. Once the frill opens, hiding is over. That is what makes the species so interesting. It looks theatrical to us, but its drama is practical. The display is not made for our imagination, even though it easily captures it. The famous fictional frilled Dilophosaurus in Jurassic Park borrowed from this same visual language. The sudden neck fan, the open mouth, the shocking transformation from small shape to prehistoric threat. But in the real Australian woodland, the frilled lizard does not need movie monster abilities. Reality has its own version of the scene, and it may be even better because it is honest. This animal is not pretending to be a giant because it is foolish. It is pretending because sometimes pretending works. As the heat climbs, the lizard settles back against the bark. The frill folds neatly against its neck, almost disappearing again. The mouth closes, the body flattens. In a few seconds, the dinosaur-like apparition becomes a camouflaged reptile on a tree, watching insects move below and shadows pass overhead. The spectacle is gone, but the lesson remains. Evolution does not only build claws, venom, armor, and crushing jaws. Sometimes it builds timing, sometimes it builds illusion. And in the frilled lizard, it has built one of the most memorable bluffs in the animal kingdom. A small woodland reptile that survives by making danger pause just long enough for life to continue.